Swayam Prabha. Digital India. Educated India.
Welcome to the lecture number 38 on cryogenic engineering under the NPTEL program. So, taking from where we left earlier, in the earlier lecture, we talked about conductance. We talked about the conductance equation that has to be considered in order to calculate the pumping speed. And we had talked about various conductance equations for some commonly used pipes. We also know the concepts of pumping speed SP, and we know the meaning of the word system speed or SS. So, the pumping speeds will depend upon throughput and the pressure, the vacuum you get at the inlet of the pump, while the system speed is basically due to this conductance plus the pumping speed, and therefore, the system speed is going to be less than the pumping speed and it is equal to Q upon P, that is what actual vacuum you get, which is going to be less than the PI value. Now, this SS and SP, the system speed and the pump speed gets related to each other, and we have seen this equation 1 upon SS is equal to 1 upon SP plus 1 upon CO, where CO is the conductance of the connector of the vacuum pump and the system to be pumped. So, one can see from here, this is a kind of a reciprocal rule. We know that SS is going to be less than SP and less than CO. So, in order to maximize SS, we have to use such a pump which has got a maximum CP, and we have to use such an arrangement we get maximum conductance, so that our value of SS is going to be as high as possible. So, one can see from here, from this equation, and also we know that SP depends on vacuum pump. So, what kind of pump do we use? The vacuum pump actually will decide what maximum SP it can deliver. So, therefore, one of the most important variable in order to calculate system speed is SP, while CO is going to be depending on arrangement or how easily one can access the system. Can I use big diameters? Can I use minimum of curvatures? Alright, all this will decide in order to maximize conductance, and that has to be done. In a good vacuum system design, the CO has to be kept very as much high as possible. Normally, it will get governed by the geometrical placements or the configurations and things like that. However, the most important component is SP, and this SP will be governed by what kind of vacuum pump you choose. Now, this vacuum pump will be chosen based on various parameters, which is cost, time, space. All these parameters will decide what kind of vacuum pump you want to use, and this is what we are going to see in this lecture. Also, we had seen once we got a SS value, it will also decide the time that you require to create vacuum. So, depending on the volume availability, how much volume you have to vacuum, and what is your SS. So, higher the SS, less is the value of Tp, that means time to reach a particular value of P2 from the pressure P1, while Pu is the ultimate pressure. All these things we had seen in the earlier lecture. So, this particular lecture is going to be actually, decide what kind of SP we can get, and therefore, what kind of vacuum pumps that one should use. So, we will understand what are different available vacuum pumps, and depending on your requirement, how you choose different vacuum pumps. So, outline of this lecture is classification of vacuum pumps. So, vacuum pumps can be classified based on, there are various vacuum pumps available depending on their functioning, and therefore, we have to understand how do they get classified. Then we got various types of vacuum pump under each classification mode, and therefore, we will try to take an example of each of the working of different systems that could be normally used in these applications. And finally, conclusion lecture of this vacuum technology topic. Now, introduction to this topic. In the earlier lecture, we have seen the importance of vacuum in cryogenics. We have also seen the importance of degree of vacuum and the pump downtime from the application point of view. For practical applications, a wide variety of pumps are used to achieve the desired vacuum, because there are several kinds of vacuum pumps available, and therefore, based on applications, based on availability, we have to choose a right kind of pump. That this choice of pump is very important in cryogenics. There is a need to study the different types of vacuum pumps and the components of a vacuum system. This is very important to understand what kind of vacuum pumps you select for your operation. And therefore, how do we classify vacuum? How do these vacuum pumps, in what way they work? What kind of vacuum levels they can create and things like that. These are very important. How much time do they take to reach a particular vacuum? These are very important parameters, and based on this parameter, the selection of vacuum pump is done. So, the classification of vacuum pump is the most important thing to understand, and the vacuum pump is basically classified in two parts, and that is depending on how do they transfer gas, how do they create a vacuum. So, any space, if you got a space over here in which you want to remove this gas and create a vacuum. So, there are various ways of how this gas will be taken out from here, and these two ways are: one, the gas will be taken out from here and left to the atmosphere. That is one possibility, that you just take out the gas and put it back to the atmosphere basically. While in other case, which is an entrapment, the classification based on gas transfer is one thing in which gas is physically taken out from that place and dumped it to atmosphere. The second possibility is you don't take the gas out of it. You just trap the gas then and there only. That means the gas will not be allowed to move now. It will be just trapped, and therefore, there will not be any motion of gas. The gas will be kind of absorbed or adsorbed over there, and therefore, gas will not be present in the working space. So, in this case, we are not transferring the gas out of that system. The gas is kept in the system itself. It is trapped over there. So, there are two major ways in which vacuum pumps can be classified. Now, if you want to understand, there are various ways of gas transfers. Gas transfer I will do by taking this gas out from the system and dumping it outside. How can I do that thing? One is positive displacement. This is a very standard way of pumps which you see, which delivers waters to your houses basically. You just take a water from the tank and deliver it top of the house. Similarly, I will just take this gas from the system using a positive displacement. That means I have got some positive way, some directional dependence. For example, some simple compressor. You got an inlet valve, you got an outlet valve. This gas transfer therefore will happen because of some movement of some rotor element. There will be something which is moving. It will just displace this gas from this system to be vacuum and dump it. It will give the direction to it and dump it to the atmosphere. It will try to dump it to the atmosphere or try to dump it to the next pump, which ultimately it will leave it to the atmosphere. So, positive displacement pump will basically take this gas from the system. It will create actually a pressure difference, because of which pressure difference the gas will be taken out from the system. It will be given a direction, correct direction, so that it goes from system A to system B and directly from system A to the atmosphere. Sometimes it can go from system A to system B and it can go to atmosphere. So, here creating a direction, taking this gas from the system and dump it to the atmosphere, this is what we call as a positive displacement type of gas transfer. The other one is, you got several gas molecules over there, and it is not possible for you to give a direction in this case, because now we are talking about molecular levels. In this case, what we do is, give a direction to the molecules, give velocity to the molecule in a correct direction. Alright, so each and every molecule is actually bombarded with other molecule, maybe of gas or a fluid. It will give its kinetic energy to that particular molecule. That means the momentum will be transferred, and therefore the molecule will travel, and the travel will happen so that the gas molecule goes out of that particular system, creating a vacuum over there. So, these are the two different ways of gas transfer, and under each type now there are several kinds of pump. For example, under positive displacement pumps, we got 4 different characteristics of pump, which is sliding vane type of pump, we got a rotary vacuum pump, we got a roots pump, and we got a dry pumps. So, in which all these cases there is something which is moving, and this moving element will move this gas from the system to be vacuum to the atmosphere. And we will see for example, the rotary pump and roots pump, how do they work, and in the similar fashion all these pumps normally would work. Now, under kinetic kind of vacuum pumps, kinetic, as I just told you, that the velocity is important, therefore momentum is transferred from molecule to molecular level. Most of the times kinetic kind of vacuum pumps are used for molecular levels. So, in which category we have got a diffusion type of pump, we got a turbomolecular pump, and we got a fluid entrainment pump. So, there are 3 different types, of which we will talk about diffusion and turbomolecular pumps in detail to understand how do these function. The third category or the second category of vacuum pump, which is based on entrapment, these are all the types which come under gas transfer pump. The second possibility is to have trapping of these gases. That means the gases will not be physically taken out from the system, but they are trapped inside the system only. Under this category now, we got several types of pumps again, we got absorption phenomena, where the gases are just taken over and absorbed over like a sponge basically. So, the gases are retained over there only, they are just absorbed. Then the cryo pump, here the gases are, the temperature of the gas is lower to such a level that they get solidified. All right. So, they get sort of dumped over there, they can't move, and therefore, the vacuum gets created. Then we got a gator where adsorption phenomena could be utilized, or there could be chemical action, because of which this gas molecule will cease to move and they will get kind of, some chemical action may happen and they will get trapped over there. So, we got 3 different ways of having to trap this gas, and we got 4 different ways of having gas transfer by positive displacement type. Again, we saw that under the kinetic category, we got 3 different pumps. So, this is the overall classification structure. One has to understand, is it a gas transfer type or entrapment type? Naturally, you can't trap a lot of gases. You cannot trap a big number of gas molecules over there. So, there is a limitations, but the gas transfer can happen continuously, and therefore, this is the most acceptable kind of mechanism that is normally used in big systems. While entrapment is to improve the vacuum further. If you go to -5, to go from -5 to -6, normally trapping would be done. Now, let us see an example, how does a rotary pump work? We can see few examples like rotary pump, Roots pump, diffusion pump, turbomolecular pumps, cryo pump. These are the pumps which are normally used in most of the engineering applications. So, let us see how does a rotary vane pump works. So, rotary vane pump is a widely used pump in vacuum technology. In most of the applications, primary applications, rotary vane pumps will be used. It is mostly used as a primary pump for backing or roughing stages. That means you can get a -2 or -3 levels of vacuums, which are sometimes used as backing to other pumps, or you can get some rough vacuum of -2, -3, and then afterwards you can use different pumps. This is called as a vacuum kind of a pump, or you can create a rough vacuum with these pumps. And obviously, this pump falls under the category of gas transfer and positive displacement. It is what we just talked. So, it falls under the gas transfer category with positive displacement characteristics. That means, it has got some directions from where it is taken and delivered to atmosphere. So, how does a rotary pump work? What is the principle of working of a rotary pump? So, this can be shown in this schematic over here, and we can understand how does a rotary pump work. The schematic of a rotary vane pump is as shown in this figure. So, it consists of a stationary part, stator, which is what you see here. The blue colored is a stator, it does not move at all, while there is other component which is called rotor, which moves in this stator. So, it consists of a stationary part, stator, and a moving part, rotor, assembled inside the casing. So, this is the casing to which we call as stator, and this rotor which is actually attached to a motor which will rotate this, but you can see this rotor is little eccentrically placed with this. All right. So, this is what constitutes a rotary pump. Moving component is an eccentrically placed slotted rotor. This rotor is not a simple rotor, it has got a slot, and through this slot runs a vane, and this is what we can see here. So, moving component is an eccentrically placed slotted rotor which turns inside the cylindrical stator. So, why eccentricity? You can see that there is a sealing, there is actually some kind of seal contact between this rotor and stator. So, this is inlet of the gas, this is exit of the gas, and this inlet of the gas cannot go directly to the exit, it has to go through this way only, and therefore, this is kind of sealing. Therefore, for which case you have to minimize the distance difference of the opening between the stator and the rotor. There should not be any gap left over here, and therefore, this rotor is eccentrically placed with this stator, and whatever gap remains there is actually sealed with the oil which is present over there as a lubrication also. So, there is no rubbing as such over here. It is a rolling contact between the rotor and the stator. Alright, these spring loaded sliding vanes are mounted in the slots of the rotor. So, you can see the rotor over here, and there are slots in this case, and these slots which will have a sliding vane, and these sliding vanes are spring loaded. So, there is a spring inside which sees to it that these vanes are always in contact with these walls. So, actually they get rubbed on this wall, and the spring which are in tension sees to it that this vane is always hard pressed against this stator. Alright. So, because spring loaded sliding vanes are mounted in the slot of the rotor. So, when this rotor will rotate, these vanes will rub against these walls, but they will never cease to be not having contact with this stator, always be in the rubbing contact with this stator. This rotor is driven by an electric motor at a constant speed. So, the rotor is driven by a motor which rotates at a constant speed. Due to the spring action, the rotor sliding vanes are in continuous contact with the stator walls during the rotation. This is what I just told you, that this spring will ensure that the vane is always in contact with these walls. This rubbing action generates huge amount of heat naturally, and therefore, we need to have some kind of cooling mechanism. The heat is dissipated by circulating coolant around the stator. So, you can have some oil or some kind of air or something, some cooling medium will always be there to cool the rubbing, the heat which is generated due to rubbing. Now, how does it work? So, the system to be vacuum will be connected to the inlet of this pump, and air which is got a working medium, we can say it is drawn over here through this inlet, because as soon as this rotor start moving, the pressure which is going to be generated at this point is going to be less than the atmospheric pressure which is existent over here. So, as soon as that happens, this air at atmospheric pressure will start coming inside. Why this happens? Because the rotor is moving all the time, and this vane sees that there is no gas left inside. In fact, all the gas trapped between this space over here is basically going to be given to the outlet from here. So, as soon as the rotor starts moving, the air is drawn due to less pressure on this side, the air comes through this inlet and enters over here. Spring loaded exhaust valves are used to expel this compressed gas. So, now once the gas comes, when the rotor is at this point, the air will come here, and when they start rotating, this gas volume which is over here now between these two vanes, it will get compressed, and by some time when it reaches near the exit, the pressure here will just get above the atmosphere. As soon as this pressure gets above the atmosphere, the exhaust valve which will just open. As soon as it reaches some pressure above atmosphere, it will open and the air will be released to the outlet. So, this sees to it that the gas comes here, it start getting compressed, just getting compressed above the atmosphere, opens this exhaust valve and gets delivered to the outlet, to the atmosphere through this outlet opening. So, this valve operates only at a preset pressure to avoid the backflow. So, gas cannot come back. Therefore, this pressure on this side is going to be just above a predetermined value where the exhaust valve opens and it is delivered to atmosphere. Perfect sealing is maintained by a thin fluid film existing between the moving contact. So, there is a moving contact at this point, and therefore, you have to see that there is oil over here, and this sealing is maintained by maintaining this clearance between this rotor and the stator, and it also ensures that the gas or the air which enters over here does not move on this side. It always comes through this, it gets compressed and then delivered to outside. It is important to note that there is the possibility of condensation of some gases, say water vapor, during the compression process. Now, this is very important because the air will always come with some water vapor, and if the water vapor because it gets compressed, it has got a particular dew point at its pressure, at its partial pressure, and therefore, this water can get condensed over, which is not acceptable. In a reciprocating or a rotary motion, you can't have a water which is going to get condensed at this point, and therefore, you have to ensure that such a condensation should be avoided in this case. So, in order to avoid this condensation of the water vapor or any condensable matter for that case, this should be avoided over here. So, what is done for that? We got something called as gas ballast valve. Gas ballast is an arrangement in which a metered amount of non-condensable gas is admitted at the high pressure side. So, what we do? We admit some high pressure air from this side or non-condensable gas here at this point, and because of which this is a non-condensable gas, the partial pressure of the condensable gas which will come down. Alright. So, please understand this, that I am admitting some non-condensable gas is admitted at this high pressure side at this point. This gas packet increases the mole fraction of non-condensable gases in the compressed space. That means, it decreases the partial pressure of the condensable gas. Once you decrease the partial pressure of the condensable gas, the corresponding dew point for that, the temperature at which it condenses will get lowered, and therefore, at this prevailing temperature, the condensation may not be possible because the partial pressure of this condensable gas gets reduced. So, what is done to do this? We add some gas, increase the pressure of the non-condensable and decrease the partial pressure of the condensable gases, because of which now it can't condense anymore, and then therefore, it is delivered out in the gaseous form itself. This decreases the partial pressure of the condensable gas, alright, and therefore, as a result, the water vapor at this temperature does not condense. The very important function of the gas ballast, especially in a place where humidity is very, very high, there is always a good possibility that the water vapor is there in the air, and therefore, initially for some time when you start the rotary pump, for some time the gas ballast valve is kept open, the air is admitted at this point, and after some time when the moisture in the air gets removed, the gas ballast valve can be closed, or sometimes it can function throughout the operation of this rotary pump. So, these are the characteristic of the rotary vane pump. We can see the speed versus pressure. Alright, the adjacent figure shows the pump characteristic for single and two stage rotary pumps. The solid and the dotted lines corresponding to pumps. So, you can see solid line and a dotted line. The solid line is with ballast. So, as soon as you got a ballast, that means the ballast is on, you got a gas coming or the air coming from the outlet side, because of which your capacity goes down. So, you can't deliver low vacuum in this case, because you are adding some air deliberately from outside. While if you go without gas ballast, then you can deliver good vacuuming rate and you can come down to lower pressures also. At the same time, such pumps can be used in two stages also. That means the outlet of the first pump will go to the inlet of the second pump. In that case, your meter cube per hour, that means the vacuum speed can be increased. You got around 10 meter cube per hour in that case possible, and also that you can reach lower and lower pressures in this case. So, one can go for a two stage rotary vane pump, one can go for a single stage rotary pump, one can have the gas ballast on continuously. In that case, one can have these characteristics, or one can start the pump keeping the gas ballast on, and after some time when the condensables have been taken care of, then the gas ballast can be made off and one can then get good vacuum. That is what is shown without ballast. Alright. Two stage or multi stage pumps are used to improve the performance and the ultimate pressure PU of the systems. So, this is the way how the rotary vane pump will work, and this is the characteristic of the rotary vane pump with single stage and two stage arrangement, or with and without gas ballast. This is what we have seen now. We saw the rotary pump. Let us see now the second pump, which is a roots pump. That is also normally used where you require high flow rates, or you want to reach lower vacuums in a very, immediately. That means less time could be taken in those cases. So, a typical rotary pump, rotary roots pump would look like this. So, you got an inlet and outlet arrangement, and you got a two lobe arrangement. This is a lobe number 1 and lobe number 2. This kind of arrangement is done in a roots pump. The schematic of roots pump is as shown in this figure. It is often used for low and medium degrees of vacuum. So, roots pump are used at various places, but not for very high vacuum requirement. Most of the time the roots pumps are preferred in order to reach vacuum very fast, because the vacuuming rates here are much faster. The pump is best suited in applications where there are high mass flow rates. So, if you want to have very high mass flow rates, or you want to have a very big system to vacuum, one can use roots pump. Sometimes this rotary vane pump may not handle very high mass flow rates, or you may have to employ 2 or 3 pumps in those cases, while around 500 meter cube also can be handled by roots pump basically. It consists of, how does it operate now? It consists of 2 identical lobes, rotor mounted inside a casing, which you can see these 2 lobes. Actually, it has got kind of a 8 shaped over here. So, there are 2 lobes, we have got a 8 kind of geometry, and both these lobes are actually rotated in opposite direction. These lobe rotors are synchronized by an external gear mechanism and are connected to an electric drive. So, both of them are driven by using electric motor, and they are synchronized. That means they got a spatial relationship existing between their rotation, and this synchronization is done through some external gear mechanism. A fine clearance of 0.3 millimeter is maintained between the moving lobes and the stator. So, you can see that there is a very fine clearance between these 2. Also, you can see there is a very fine clearance between the casing and this rotor, and at this point, and therefore, the fabrication of these lobes is very important. The cost of these pumps are relatively higher because of the fabrication costs also involved in them. The micro fabrication, that kind of thing which is required, the high tolerances that is need to be maintained, these are very important over here. They should never touch each other basically. If they start rubbing on each other, then it will lead to some kind of failure of the roots pump. As a result, these pumps can be operated at a very high speed. Now, the fact that there is no rubbing contact, in the earlier case there was rubbing contact of vane. Now, the fact that there is no rubbing contact, there is always some clearance, they can rotate at a very high speed also, and this high speed is responsible to have that its ability to handle very high mass flow rates. So, actually they will never basically have a rubbing contact, they can move freely, and therefore, we can operate these at very high speeds, and this is a very important characteristic of roots pump. The lobes are rotated in opposite direction with respect to each other. This is what you can see. So, basically it will take this gas from inlet and deliver through this to the outlet, and during which it will get compressed. The gas here also the gas can come through this also, and the gas will be delivered from inlet to the outlet, from the system to be vacuum to the atmosphere. The gas is displaced from inlet to outlet, maintaining a pressure drop. So, the movement of the gas is basically going to happen because of the pressure drop that exists across the inlet and outlet. Alright, and the gas is going to get compressed while traveling through this, and normally the compression ratio could be of the order of 10. Sometimes if you want to have high flow rates, for example, or if you want to create low vacuum, a backing pressure is necessary on the outlet side before the operation of the pump, so that you can create a kind of a pressure difference across, and these pumps can be put into operation, and then by which you can really reach lower vacuums also. This is needed to prevent the overheating. Sometimes when there is no flow occurring, there is no delta P across, then it can create a lot of heat over here because of the motion. The gas is getting compressed, but gas is not moving. The gas will move only when the pressure difference exists across the lobes basically. So, in this case you can have a very high heating over here. This is needed to prevent, and therefore, when the gas starts flowing, the gas also does cooling. So, it is not good to have the gas just moving over here. Gas has to transfer across here, and during that time it cools these lobes also. Alright. So, the viscosity of the gas also plays a very important role in creating heat in the Roots pump operation. The overheating of the casing results in thermal expansion. If that happens, it will result in thermal expansion of lobe rotors, and thereby the possible contact between the moving part, and this should be avoided. If this starts having contact between these two, this can't move, and it will result in failures of Roots pump. It is important to note that against this high mass flow rate, one has to compromise on vacuum level. So, if you got a very high mass flow rate, you will not get good vacuum. You cannot get to very low vacuum case. In that case, you can get rough vacuum, and you can have very high mass flow rates in the Roots pump. That can be seen from here also. This is the Roots pump's characteristics. You can see that the adjacent figure shows the pump characteristic for a single stage Roots pump. Initially, the pump speed AC increases steadily. So, as the pressure vacuum increases, the speed will increase, it reaches to a maximum value, and after the vacuum is created, if you further increase the vacuum level, the pumping speed decreases in that case. Alright. So, one can operate at a very high speed at this point, but you get less vacuum in this case. So, one has to see a compromise between the pumping speed and the kind of vacuum. If you want to have very high vacuum, then the pumping speed is going to be comparatively less. With a further decrease in the pressure, the pumping speed goes through a maxima and then decreases. So, you have to decide at what pressure you want to operate. If I want to operate only at 10 to the power minus 1 millibar, then I am going to have a very high pumping speed, and therefore, this is where almost 100 meter cube per hour, or you can go to 200 meter cube or around 500 meter cube per hour also, which is a very high speed as compared to that of the rotary vane pumps. And therefore, Roots pump are normally used in applications where very high pumping speed is required at relatively low vacuum levels. Alright, so this is what we talked about Roots pump. So, we have just now talked about rotary pump under the positive displacement, also we talked about rotary pump. Now, let us go to kinetic kind of pump, and let us talk about diffusion pump in this case. It is a very important pump, and we have been using diffusion pump in almost all the operations here, alright, because kind of applications we have, the diffusion pump is successfully delivering us the vacuum of -5, -6, that is what required. Also, at the same time, it is not very costly, and it can be maintained in the lab atmosphere. Alright, so let us see how this diffusion pump works. As we know that the diffusion pump falls under the category of kinetic pumps now. So, kinetic pump, I just told you that it works in a molecular level, and it basically involves transfer of momentum from fluid A to fluid B. So, kinetic pumps are used when a high degree of vacuum in comparison to rotary or Roots pump is needed. So, I am talking the rotary pumps, Roots pump delivered normally the vacuum of -2 to -3. While if you want to go to -5 and -6 torr, 10 to the power -6 and -6 torr, we will have to look at now kinetic pumps, and therefore, these pumps work at molecular level. They work not in the continuum region, they do not start from the atmosphere, they start at -2 or -3. Their working starts once the molecular levels have been achieved. In these pumps, kinetic energy or momentum is imparted to a gas molecule, what we talked. This momentum is used in expelling gas molecule from the system, and thereby vacuum is created. So, the system to be vacuumed, all the gas molecule will be imparted momentum, so that these gas molecules are driven outside. As mentioned earlier, diffusion pump, turbomolecular pump, fluid entrainment pumps are the common example of kinetic pumps. Now, this is a schematic of a typical diffusion pump. Let us see now how does a diffusion pump works. The schematic of a diffusion pump is as shown in the figure. It consists of a chamber housing a oil vessel, we can see over here. This is the chamber I am talking about, and there is the oil at the bottom over here, and there is a heater at the bottom to heat this oil. So, it consists of a chamber housing a oil vessel with a heater, a chimney which is over here, alright, you can see a chimney over here, a chimney and a nozzle which is at the top. So, you can see a nozzle. So, you got a chimney over here and a nozzle at the top. On chamber outer surface, cooling coils carrying water are wound. So, you can see on this side, you got a cooling coil. So, this is basically the coiling is done through which the water is flowing. Water at room temperature, chiller water, whatever water, it is going to be flowing all the time. So, whenever you want to operate diffusion pump, you require this water connection all the time. These pumps are most effective when operated in free molecular regime. As I was telling you that these pumps normally look after molecules, they will impart momentum to molecules, and therefore, they cannot be started in the continuum region, or they cannot be started working at atmospheric pressure. They can't start having vacuum, creating vacuum from atmospheric pressure. So, in practical application, it is coupled with a backing pump. So, some kind of pump is used over here, which will first create kind of a molecular region, and then these molecules are dumped to a backing pump, and this backing pump will leave it to atmosphere. So, this is the way the diffusion pump would work. The heater, now how does the diffusion pump work? So, suppose I want to create vacuum in a system which is kept at this point, and the diffusion pump will be attached to that system to be vacuumed. I will start the heater vaporizes the oil. So, this oil will be vaporized depending on vapor pressure, it will get vaporized, and this oil will travel up to the top, the molecules will go up, the hot vapors will go up, and they will start coming out through these nozzles. The heater vaporizes the oil, and these hot vapors rise into the vapor chimney. The hot vapors are deflected downwards by an annular nozzle or a jet assembly mounted at the top of the chimney. So, you can see the nozzle at this point, and the hot vapor will go up, and they will come at a very high velocity when they travel through these nozzles, and that is the work these nozzles would do, or a jet assembly would do. This jet moving downwards at supersonic speed imparts momentum. These vapors which come out of this actually will impart momentum to all this gas molecule present over here. The system to be vacuumed over here, and there is a gas all around here, and when this gas comes out, this gas will impart momentum to all these molecules here, and therefore, this molecule will be given direction, and this molecule will be traveling, and they will hit these walls. These vapors moving downward at supersonic speed imparts momentum. This jet of the oil vapor which is coming out, it will impart momentum to randomly moving gas molecules in the chamber. So, you got a gas molecule which is moving here, and this jet of the water vapor will impart momentum to these molecules, and they will give direction to this randomly moving gas molecules. This momentum deflects the molecule toward the pump outlet. This is the pump outlet. So, all these gases will try to come towards the pump because the momentum has been given by this high velocity jet. In other words, this momentum gives direction to the randomly moving molecules toward the pump exit. Now, having delivered them to this is a backing pump which will take these molecules at this pressure and deliver it to atmosphere. It will compress this molecule to dump it to the atmosphere. So, the backing pump is very, very important because the diffusion pump works in a molecular region. So, it will take this molecule from here and dump it to some pressure, from where it is further compressed to atmosphere by backing pump. So, a backing pump is constantly used to remove the gas molecules. What would happen if I do not use backing pump? You can have all the molecules at atmospheric pressure here, which is a very high pressure at this point, and there are such a big number of molecules will be there that this water vapor will not be able to strike to those molecules at all. So, that is why you have to have a molecular region over here and not a continuum region, because there are plenty of molecules in other case. Alright, so you have to create a molecular region so that each and every molecule gets addressed by this jet which is coming out of these nozzles. The hot oil condenses. Now, what happens to the oil? The oil vapor which is coming at a very high speed, it brings this gas molecules to the outlet, while this the oil when it touches this wall will get condensed because of this running water from outside. Alright, so hot oil will come over here, it will get condensed because of the running water at this point, and therefore, it will again condense back and will come back in this oil at the bottom of this chamber again. So, hot oil condenses on cold wall and returns to the vessel at the bottom, and again it will get heated, the vapor will start up, it will get velocity when it comes out of this thing, it will impart momentum to the gas molecule and come back, and this cycle continues. One of the common problems in the diffusion pump is the backstreaming of oil. So, sometimes when this oil gets heated, this oil can go in the space to be vacuumed also. This is a very important disadvantage which has to be considered while using a diffusion pump. So, if your system can handle sometime the backstreaming of this oil, which has got a good possibility to come in the system itself, then this system, the diffusion pump cannot be used. Alright, because diffusion pump handles oil, and sometimes the equipment, for example, in semiconductor physics or microelectronics, they can't afford to have any oil coming in the system. So, in this case, diffusion pump cannot be used. So, this is a disadvantage of a diffusion pump, that sometimes the backstreaming of oil is possible. This occurs when the pump oil molecules move above the upper portion of the jet. This causes contamination of vacuum chamber. This is not permissible for certain applications, and therefore, in those cases diffusion pump cannot be used. Now, this also can be avoided to an extent. So, one can have some chilled baffles over here, and these baffles are chilled with running water or using liquid nitrogen sometimes. So, this chilled baffles or cold trap is used to prevent the flow of oil molecules into the vacuum chamber. So, suppose at all oil is traveling, it will get trapped by this cold trap, which is cooled by liquid nitrogen, or chilled baffle, which is cooled by chilled water, and this oil will get condensed over here. This oil vapor, which otherwise would have gone to a system, can get condensed and it will come back over here. So, one can always use a diffusion pump with a cold trap in order to minimize the backstreaming of oil in the system to be vacuumed. Alright. So, there is a disadvantage associated with it. At the same time, this disadvantage can be taken care of partially to a greater extent by using chilled baffles or cold trap. However, in a system where it requires very clean vacuum, where some traces of oil also cannot be allowed, in that case one cannot use a diffusion pump. So, choice of a pump will be dictated by the kind of applications you are using it for. Now, this is the characteristic of diffusion pump, that as soon as it works between -2 to almost -6, -8 millibar region, and the speed remains constant. Alright. The figure shows the variation of pump speed with pressure. Alright. So, you can see 100 meter cube per hour or 150 meter cube per hour, that kind of speeds diffusion pump will have, and you can go up to -8, -7 kind of pressures, which we have been talking about. The ultimate pressure PU, what limits this pressure is basically the vapor pressure of oil. At what particular pressure the oil get evaporated, what is the vapor pressure of oil, that also will decide what is the limitation on the pump pressure basically. Then pump design, of course, what is the characteristic for what particular pressure it has been designed for, and again the gas load from the vacuum space. If you got a very high gas to be removed, gas load, it will take a lot of time first thing, and you cannot reach very low vacuum in those cases. The schematic of a diffusion pump together with a rotary pump is as shown in the next slide. So, how does it work? Because it has to work with a backing pump, and one can see a schematic. So, you can see that this is my vacuum chamber to be vacuumed, and you can see that this is the diffusion pump, and this is the rotary pump, and this rotary pump is connected directly to the system to be vacuumed through this roughing valve, and also it is connected to the diffusion pump through a backing valve. As mentioned before, diffusion pump is effective in free molecular regime. The initial pump down of the system is done using rotary pump. So, you can't start diffusion pump immediately if this vacuum chamber is at atmospheric pressure. So, in which case I will not start diffusion pump, but I will start only the rotary pump. And this rotary pump, when it is attached to the vacuum chamber through a roughing valve, it will create the -2 or -3 levels of vacuum before the diffusion pumps comes into action. Alright. So, with a backing pump valve close, in that case what will I do? I will close this backing valve, that means rotary pump connection with diffusion pump is stopped. Rotary pump directly enacts with, it gets aligned with the vacuum chamber, and roughing valve is made on. Backing valve closed and roughing valve opened. In this position respectively, the gas is pumped out from the system as shown in this figure. So, directly the rotary pump is attached to the vacuum chamber, it will create -2 vacuum, this is delivered to atmosphere, you get around -2 to -3 vacuum. Alright, and then when the pressure in the system falls well below to ensure a free molecular regime, the diffusion pump is put to use now. And once diffusion pump comes into picture now, I will start this direct connection of rotary pump to the vacuum chamber, but I will have connection through backing valve now. So, the diffusion pump will be made on, the diffusion pump molecules comes into molecular region, it will leave this using this backing valve, it is dumped. Now, the rotary pump is acting as a backing pump to the diffusion pump, as the action of which I have explained earlier. So, with backing valve open and the roughing valve closed positions respectively, the gas is pumped out of the system as shown in the figure. And this is how the diffusion pump will work continuously now in this operation. Initially only for some time, say 1 hour, you will have a roughing valve open, the rotary pump will be directly connected to the vacuum chamber to be vacuumed, but after 1 to 1.5 hour, the roughing valve is closed, the backing valve is opened and the diffusion pump is made on, and this will start working like this. Now, you can see the actual diffusion pump over here. I have just given a picture, and you can see this is a diffusion pump here and this is a rotary pump, and they are connected through these two valves, and this is the roughing valve. I have just shown you a schematic, so you can understand it better way. So, initially I will start this rotary pump, connect it to the space to be vacuumed to this roughing valve, and then I got a backing valve which I will open once the molecular regime is established at this point. And you can see the diffusion pump, and this is the cooling coil at this, and you got a oil and a heater at the bottom over here. All right. So, one can understand entire working of a diffusion pump from this, and you got a rotary pump over here. All right. So, this will make you understand the working of a diffusion pump completely. So, let us see a video here which shows you two hoses, vacuum hoses A and B, let us say. And as I said that your vacuum pump can stay away from this place, well, your space to be vacuumed can be quite away, and therefore, we have to have some hoses joined together, for which we have got some coupling mechanism, and this is very important because this one has to be used this quite often. So, what it has got some kind of sealing in between. So, you can see some rubber sealing, you got some brass ring on which this rubber sealing goes and it stays over there. So, kind of a housing over here, and then you got a coupling, all right, and this is what constitute a kind of KF coupling here, which is normally used in connecting these vacuum hoses which are made of stainless steel, and you can see some corrugation also here, and this is the way the coupling is actually compiled together. So, you got a nut at the end which actually puts them together. So, we just saw the coupling 1, 2, 3 part, and now you can see vacuum hose which has got a diameter, and this can be a KF 25, that means the 1 inch kind of a thing. Similarly, you got a 2 inch coupling also. So, whatever you want to use, and you got two hoses now, and using this coupling now we want to connect these two vacuum hoses. So, you can see how the rubber is held on this brass housing, all right. This will have the same ID as this, and this will now be connected with this using this coupling together, all right. So, let us go ahead. So, this is my sealing, this is the way you press it now here. So, this will have a ID matching over here, the internal diameter will match with this, all right, as you see. So, this is in perfectly aligned with this vacuum hose on this side and the vacuum hose on the other side also. So, I can put them together, and now this coupling will hold all these three elements together, vacuum hose 1, vacuum hose 2 and the sealing material together. So, this is the way a KF coupling would be assembled, and this is what will be used everywhere in all the cryogenic experiments. And therefore, the conductance of the entire connection now will change because you have got two lengths brought together because of various reasons. And this is the way the two hoses of 1 meter lengths will be connected. At the other end, you got a pump, and the other end you got, let us say, some vacuum jacket, of which you have to take a vacuum basically. And this is the way the two vacuum hoses will be connected without having any leak through this, with perfect sealing mechanism, all right. So, this is our classification table, and having seen how the diffusion pump works under the category of kinetic kind of pumps, let us see now how the turbomolecular pump works, because these two pumps are normally very widely used under the kinetic category, so as to obtain a vacuum level of -6, -7 of these sorts basically. So, let us see how this turbomolecular pump works. The schematic of a turbomolecular pump, normally it is referred to as TMP. In a short form, a lot of people will call it as use a TMP. So, a turbomolecular pump is normally called as TMP in colloquial language, and this is the way it works. So, you got a arrangement like rotor, stator, rotor, stator, rotor, stator, like that. And the rotor stator would look like this. There are blades which get identified as rotor, there are other blades which get identified as stators. and they got several rotor stator arrangements. The gas is transferred and delivered to the vacuum pump, and this is how a turbomolecular pump works normally. So a turbomolecular pump consists of alternate layers of stator and rotor discs. The rotor rotates at a very high speed. The stator remains constant, stator will not move, while the rotor will start moving, and the rotor rotates at a very high speed, typically of the orders of 27,000 RPM and above. They are working at 60,000, 70,000, 1 lakh, that kind of RPM. Higher the speed, better it is, because as I told you, this is a kinetic category and is a transfer of momentum. So depending on the gas molecular size and depending on the kind of speeds they get, the mass into velocity, is a momentum is going to be created because of the mass into velocity. The typical gases which we use here could be air, nitrogen, helium, and each gas would have its own mass. To this mass now we will give a momentum by giving a velocity, and therefore the velocity has to be as high as possible. So speeds at which these people work, the turbomolecular pump works, is going to be very, very high as possible. That is possible from design point of view. So higher the speeds, higher the momentum. Higher the gas molecular size or mass, higher is the momentum. So helium, for example, is a very light gas, very small size molecule, very small mass, and therefore momentum transfer in that case is going to be less as compared to that of nitrogen. All right. So one has always TMP will be specifying the flow rate with respect to a particular gas, because the particular gas has got a molecule will have a particular mass, and therefore it is very important to see that normally TMP or diffusion pumps where momentum transfer happens, the speeds are mentioned in terms of nitrogen or a particular gas. Now here we got a various blades, the rotor blades, the stator blades, the rotor blade and the stator blades, and the blades are mounted at an optimum angle. There is the angle over here which ensures that the space to be vacuumed, the gas is going to move in downward directions. The molecule will strike against these blades, it will given a direction by the stator blade, again it will given a momentum by a rotor blade, again the direction will be given by stator blade, in order to see that molecule will not go back but is always going down to the vacuum pump. So the direction is given by the blade angle, and the blade angles have to be correctly designed, manufactured optimum angles. And these angles have to be ensured that they correctly exist on rotors as well as static blades. Both the blades will have to have correct angle. This high speed rotation imparts momentum to the gas molecules upon collision with the rotor disc. So what is happening? This rotor is moving very, very fast, and the gas molecule will come over there, and this gas molecule will collide on the rotor discs, and during this disc the momentum of the rotor will get transferred to the gas molecule, and it will get velocity, because of which it will go to the stator, and again the stator will give direction. Again on the next rotor stage it will get a momentum, and again it will give a direction, and in such a way that the momentum is imparted in every rotor stage, while the stator stage ensure that it goes in the correct direction, and ultimately it will go through a vacuum pump. The high speed molecules are directed toward the exit using the stator discs. These two adjacent discs are often called as a stage of a TMP. For example, one rotor and one stator will constitute one stage. So you got a one stage, stage number 2, stage number 3, stage number 4, and normally 6 to 7 or 8 stages could be there for a given TMP, not more than that. All right. What is most important, you can understand that first requirement is that they are rotating at very high speed. The rotor is rotating at a very high speed, and the second is the fabrication of these blades. The angle at which each stage is kept. Every stage the angle will be different. Every stage the compression ratio will be different. All right. So the gas will come at -5, and by the time it comes to vacuum pump, the gas will be at -2 or -3 in these cases. This is very important, how this blades design will change across the stages, what the angle will change, and therefore correct angle, correct fabrication is very important aspect of TMP. The fabrication requires a lot of skills, because of which you can understand the cost of the TMP also is exorbitantly high as compared to the diffusion pump. A TMP has 6 to 7 stages depending upon the level of vacuum required. These pumps are more efficient in free molecular flow regime. Again, as you know, diffusion pump, they also work in a free molecular region, and therefore you have to have a backing pump in order to take the gas and again dumping it to atmosphere ultimately. So the TMP would deliver from -6, -7 to -2, and from where rotary pumps will take over as backing pump, and they will deliver it to atmosphere ultimately. They are often backed up by mechanical pumps or a rotary pump. A lot of developments are happening because they are moving at such a high speed. The bearings of TMP pump, all right, the balancing of TMP pump are very important research activities, research topics. The latest development in TMP include replacement of oil bearings with dry non-lubricant bearing. All right. So, you got to have lot of magnetic bearings are there, non-contact bearings are there, static bearing, dynamic bearings are the very important happenings, research activities happening in the design of turbomolecular pump. And a typical turbomolecular pump is shown over here, and you can see that there is a rotary pump on this side and there is a turbomolecular pump which houses all the stages here. All right. So, you got a turbine stages which are housed over here. You got a rotary pump which is kept at this point. So, there is a kind of a backing pump and ultimately it is left to atmosphere. This is the way the TMP works. Let us come now next kind of thing, which is I am just going to give an example of entrapment kind of a vacuum pump now, and therefore, we can see under this category we can see how a cryo pump works. So, we have seen now gas transfer type of pumps, we will see entrapment, and under entrapment now let us see how does a cryo pump work. Now, how does a cryo pump work? Cryo pump basically works in lowering of temperature and seeing to it that the gas vapor pressure is brought down. That means, the gas ceases to be in gaseous conduction, the gas gets actually frozen down because of the lower temperature that is generated by a cryo pump. So, for example, if I am at 100 Kelvin, it ensures that water is at very, very low vapor pressure now. It is as low as -9. That means, it is not non-existent at all. All right. That means, all the moisture in this case is completely frozen now. This is not in gaseous stage at all, and therefore, there is no gas existent over here. If I come down to 20 Kelvin, you can see that water, xenon, oxygen and nitrogen, all of these are below -9 kind of a vapor pressure. That means, these gases have got frozen if I got a 20 K surface exposed to these gases. So, at 20 K now, what are the gases over there? There are neon, hydrogen, helium. This cannot be taken care of. So, if I got a surface which is having a 20 K temperature, it will ensure that the vapor pressure of all these gases, normal gases which are existent in air, will be taken care of. That means, they all get frozen and therefore, their vapor pressure is much below -9. All right. And this is the basic principle on the cryo pump works, that can you lower the temperature of the space, therefore, all the gases in that space will get frozen down, and that means they get cryo pumped. All right. This is what a principle of a cryo pump is. The adjacent figure shows the variation of equilibrium vapor pressure with temperature for different gases. When the temperature is less than 20 Kelvin, the vapor pressure of gases other than helium, hydrogen and neon are close to -9 millibar. That means, you can get a vacuum pressure of -8, -9 easily, but neon, hydrogen and helium will still be in gaseous phase over there. But they are, as you know, they are the rare gases basically, but you can't take care of neon, hydrogen and helium. At 20 K, their pressures are very, very high. They could be at 10 to the power 3 millibar kind of pressures. So, typical cryo pump looks like that. It consists of a 2-stage GM cryocooler. So, you can see a 2-stage GM cryocooler which works in a closed cycle manner. You can have a compressor running this cryocooler. The first stage of this cryocooler delivers around 70 Kelvin. The second stage of cryocooler delivers cooling effect at around 20 Kelvin. And this works on a principle normally of GM type machine, which we have seen already. How does it work? The schematic of a cryo pump is as shown in this figure. A 2-stage cold head unit produces temperature of 70 Kelvin and 20 Kelvin at first and second stage respectively. Adequate shielding and insulation is provided to avoid various heat inleaks. This pump can reach pressures as less as 10 to the power -10 torr, which is very, very good. So, you can see now here, the first stage is connected to this lubed radiation baffle. That means, this baffle is kept at around 70 Kelvin and the space to be vacuum will be exposed over here. When the gas comes inside, whatever moisture is there, because this is 70 Kelvin, this moisture will be trapped, it will get frozen down. And we know that at 70 Kelvin now, all the moisture is taken care of. Now, the second stage, you can see there is a shield over here and this is at 20 K surface. So, when this gas comes down, the remaining oxygen, nitrogen, xenon, etc. will get frozen down on this. And therefore, at this 20 K, this 20 K shield will take care of the other gases other than moisture, while this 70 K shield which is connected to the first stage, it will take care of water vapor. As mentioned earlier, all the gases except helium, hydrogen and neon are frozen at 70 K baffle and 20 K cold head. So, 70 K baffle and 20 K baffle will take care of all the gases except helium, hydrogen and neon. Now, helium, hydrogen, neon are basically going to be adsorbed on the carbon charcoal paste which is kept over here on the inside part of this inverted cup. One is an open cup like this to which baffles are connected, one is a closed inverted cup and the inside part of this is going to be having a charcoal paste on this, on which helium, hydrogen and neon will get adsorbed. So, all these other gases also can be taken care of by this adsorption technique on the activated charcoal. The gases like helium, hydrogen, neon are adsorbed onto the charcoal provided on the underneath of 20 K shield, and this is the way cryopump will take care of almost all the gases in this case, and this is the way it works. Hence, it is clear that the pumping speed of this pump is directly proportional to the surface area. More the surface area, you can have more gases that could be adsorbed or that could be trapped in this case. These pumps are self-contained, hydrocarbon free and are cooled by a two-stage cryocooler. So, there is no oil business over here, and therefore, it creates a very clean vacuum, and this is the way they can be really used in application like semiconductor physics, microelectronics. Cryopump is a very acceptable pumps in this area because they deliver very clean vacuum. There is no oil like what it is in diffusion pumps. Now, there are several other pumps called, I will not go into detail, but Gator pumps, sputter ion pump, sublimation pump, adsorption pump, and I would like you to go through the working of these pumps. They all come in kind of entrapment pumps that also could be sometimes used. The pump selection is governed by various criteria, and there are criteria. What is the working process? What kind of pump do we want to use? Do I want to rotary pump, diffusion pump? As I said, we have got a clean requirement of vacuum, I should go for a cryo pump and things like that. So, working processes, ultimate pressures required, total volume, surface area of the chamber to be vacuumed, outgassing rate of the operating pressure. So, is there outgassing possibility? Is there a painting on the inner part? Is there some coating on the outer part? All these things have to be seen. Pump down time required, that is also will decide what kind of pumps that could be used. Dimensions, weight, vibration limits and cost also will decide what kind of pumps to be used. And there are sometimes special requirements like hydrocarbon atmosphere, reactive gases, bake out, which will also decide what kind of pumps do we select in these cases. So, what we have seen in general is various pumps, and various pumps have got different operating ranges. If I want to operate from here to here, -2, I can select only rotary pump. So, the adjacent figure will show the operating ranges of different vacuum pumps. So, for example, if I want to work from -2, I will have a mechanical or single stage vacuum pump, and if I want to go up to -3, I can have a two-stage mechanical vacuum pumps. If I want to go below -2 up to -6 or -8, I can go for diffusion pump. That means I will require a backing pump in order to reach up to -2 first. This is what we have seen earlier. And then I got different ion pumps which can take me down to -10 levels of torr, and then I got various other pumps like sorption processes which can bring to -6 pumps, and there are other pumps like cryo pumps which can operate from -3 to -10, giving me clean vacuum. Several other pumps are there. All of them will have their operating ranges, but what is important to see is what kind of pump to be used and what criteria of that should be used has to be understood with the working of these pumps. So, let us summarize what we have learnt in this particular topic. We have found that heat inlet is minimized by having vacuum between two surfaces of different temperatures. We also defined a number called Knudsen number, which is lambda by d. Based on this Knudsen number, we have flow regimes as continuum flow when Knudsen number is less than 0.01. We got a mixed flow when the Knudsen number is between 0.01 and less than 0.3, and we got a free molecular flow when Knudsen number is 0.3. Lambda by it basically determine the ratio of mean free path to the characteristic dimension d, and the lambda is defined as the length between the two subsequent collisions of the molecules. The various conductance correlations we had understood. The conductance correlation for a few pipes and pipe joints are given in the lectures, and we found that based on these correlations we can calculate conductance, based upon which we can calculate the pumping speed and the system speed. And we know that conductances when put in series, you got this expression, and when conductances they are in parallel, we got these expressions in order to calculate the overall conductance of these pipes in series and pipe in parallel. We know that the pumping speed SP depends on a vacuum pump, and therefore, in order to maximize system pumping speed, we know that the conductance should be kept as maximum, and SP and SS and CO get related by this formula, which is 1 upon SS is equal to 1 upon SP plus 1 upon CO. We have studied this formula in detail. For a constant SS now, we got an expression for time to create a vacuum from the pressure P1 to P2, and as SS is more, as the system pumping is more, we know that time to reach that particular vacuum is going to be less and less for a given volume V. Then we had studied various vacuum pumps. We know that the rotary when pump is widely used for backing or roughing stages. It's a positive displacement pump. Roots pump is often used for low and medium degrees of vacuum. It is best suited for high mass flow rates when you want the low vacuum to reach very fast, or we got a very big volume to be vacuumed. Then we know diffusion pumps are most effective when operated in free molecular regime. In practical application, it is coupled with a backing pump. Then we got TMP or a turbomolecular pump. It consists of alternate layers of stator and rotor discs. These pumps are more efficient in free molecular flow regime as diffusion pump. Then we got a cryo pump, which gives us clean vacuum. When the oil is a question, always a clean vacuum is preferred using cryo pump. So commercially available cryo pump has normally a 2-stage GM cold head or a cryocooler, which first stage around 70 to 80 Kelvin, while the second stage will be around 15 to 20 Kelvin temperature on these 2 stages of this cryocooler. And based on the temperature generated on this first stage and the second stages, various gases will be getting frozen on the surfaces. The vacuuming process involves freezing of the gases onto this cold end and the vacuum is generated. This is in short the summary of the entire vacuum topic. Thank you very much.